Physical optics is the main contribution to the overall scattering in high frequency. As we told at the end of the last class, you can see that the first three scattering phenomena, the three most important scattering phenomena are reflection at surfaces, and reflection at surfaces is computed with physical optics approximation quite accurately. Physical optics is based in approximating the induced currents that exist in the surface of a conductor, normally a perfect electric conductor, but if it has some losses but conductivity is high, it works well anyway. The induced current at the surface of a conductor is approximated as the current that would exist in a tangent plane, that is an infinite plane that is tangent to the conductor at that point. For example, if we want to compute the induced current here, we set an infinite plane tangent to the surface at that point, that it is in dark red color. Here this is infinite plane, and we approximate the induced current here at our actual curved surface as approximately the same current that would exist in this infinite tangent plane. The current at an infinite plane due to an incident field can be computed easily using image theory, and the result is this. The induced current at an infinite plane is twice the tangent component of the incident magnetic field, and we compute the tangent component as the normal to the surface cross product with the tangent incident field. So in fact it is a tangent component rotated 90 degrees. Okay, and observe that the normal to the surface can depend on the location along the surface, because if the surface is curved, the unit normal is not constant and it varies from one point to another. But what is very important is that we apply this approximation only to the illuminated part of the surface that is illuminated by the incident field, not the shadow region. Remember, in our analytical solutions for the cylinder here, remember that there was a shadow region where if the field is zero, if the magnetic field is zero here, the shadow region, okay, here you can observe that there is a shadow region. So in the shadow region the fields are zero, so if the magnetic field is zero, the induced current that is equal to the tangent component of the total magnetic field is also zero, since the magnetic field is approximately zero. So for this reason we approximate in the shadow region, we approximate the current as zero, and in the illuminated region we approximate the current with twice the tangent component of the incident magnetic field. Okay, so this according to this approximation, the induced current depends only on the incident field, which is the magnitude here, the magnitude and direction of the magnetic incident field, and on the unit normal, which is, well, of course, it also depends on the direction of the magnetic incident field, because the direction of the magnetic incident field determines the illuminated and the shadow regions. So it depends on the incident field, but also depends on the local geometry. It also depends on the local geometry, because here the local geometry is summarized with the unit normal to the surface at that point R. That can, as I said before, it can be different, the unit normal can be different at different points in the surface there will be different unit normals, okay? But what is important is that it depends only on the incident field and the local geometry. That is the assumption of local scattering. The assumption of local scattering in high frequency methods that we did from the beginning. The illuminated and shadow regions can be identified with this dot product. For example, for the illuminated or lit region, the dot product of the unit normal to the surface times the incidence direction is negative because they point to the opposite half space. The incidence direction points to the right and the unit normal points to the left, or vice versa, but they point in to different regions, to different opposite subspaces, okay? And on the contrary, in the shadow region, this is the unit normal here, the unit normal, the shadow region, this is the incidence direction. So in the shadow region, the dot product between the unit normal and the direction of incidence is positive because they point to the same half space. Both point to the right or both point to the left. Once that we have an approximation to the induced current, we can compute easily the far field, that is the scatter field. Remember that according to surface equivalence theorem, the scatter field is the field due to the equivalent currents, and for perfectly conducting object, the electric equivalent current is equal to the induced electric current, and the magnetic equivalent current is equal to 0. So we, in the equations in the radiation equations in the far field, that in fact are the wave, some constants times the spherical wave. Oh, this is a minus sign, sorry, here. This is, here we have a minus sign. And then we have here, this is the radiation vector, n, that you know that is the Fourier transform of the current, and this R cross is the projection into the transverse plane, the plane perpendicular to the direction of propagation, to remove the component R of the field and retain only the theta and phi components. Remember all this from chapter 1. So essentially we have the integral of the currents times the Fourier transform exponential, and the current, as we said before, is approximated as twice the tangent component of the magnetic incident field, and the magnetic incident field is the direction and amplitude of the magnetic incident field times the plane wave phase. This is the phase of a plane wave, and this is the amplitude and direction of the magnetic field, and then this is the physical optics current, etc. So it is, once we have a good approximation for the current, it's easy to compute the scatter field. In practice, for a real object of arbitrary geometry, if we have to write a computer code to compute physical optics approximation, what we do is to mesh the object. We mesh the object using a triangular mesh, or it can be a planar facet mesh. The polygonal facets don't need to be triangles. They can be quadrilaterals or polygons of more sides. However, very, very often the facets are either triangles or quadrilaterals with 4 edges. But the idea is that you have a mesh of planar facets. So you have to, in order to compute the physical optics integral, you need to sum the contribution of all the triangles in this case, or just the quadrilateral facets in other cases, but in this case you have to sum the contribution of all the triangles, and the contribution of each triangle is the integral of the physical optics current times the Fourier transform exponential on the surface of that triangle. And for any surface we can apply Stokes theorem to convert the surface integral into a line integral around the boundary of the surface. In this case there are planar surfaces, triangles, so we can just compute the surface integral. We can just compute the surface integral for a given triangle here, for example, as the integral on the edges of the triangle using Stokes theorem. And this is very convenient because we have an analytical result for the integral of the physical optics integral in the edges of the triangles or the facets. But what is important is that once that we after applying Stokes theorem and integrating only on the edges, here let's just stretch that we integrate on the edges of the triangles, it just shows that the contribution for planar facets comes really from the limits of the facet, from the boundary of the facet, that is from the surface integration limits. The equation, the formula for computing the physical optics surface integral in a planar facet is the following. You have the equation, the formula here. The different magnitudes in the formula are defined as follows. We have in this example a triangle, but it can be a planar polygonal facet. It is important that it is planar, but it can be a polygonal facet of any number of sides. R are the R1, R2, R3, R are the vertices of the facet. T are the edges, the vectors along the edges. So T1 is R2 minus R1, T2 is R3, sorry, T1 is R2 minus R1, T2 is R3 minus R2, etc. L are the center points here. L are the center points of the edges here. This Tn is the surface of the triangle, and in the case of a triangle we can compute the surface with a simple cross product. If the number of edges is larger, we have to follow a different procedure, but for just triangles we can very easily compute the surface of the triangles. So once we have defined R, T, L, etc., we have this formula for computing. This is the integral along each edge, and then we have to sum for all the edges. This eta sub 1 function is just the well-known sinc, okay? And this is a constant that goes out of the summation. So with this very simple formula, S is of course the direction of observation, scattering direction S, etc. So with this very simple formula we can write a computer program for computing physical optics. So in fact it's quite easy to identify illuminated and shadow surfaces with this criterion, with the dot product criterion, and it is quite easy to compute the physical optic surface integral with the Stokes theorem. This is called Gordon's formula, by the way. I forgot to write here that it is Gordon's formula. Maybe it was in the previous slide. Here we should write Gordon's formula. for Gordon's formula. Okay. Okay, now I see that it was here, Gordon's name. Okay. Anyway, it's quite easy. The only problem is that in real practice, when you have an object that is not convex like this, for example, imagine that you have two cylinders and the incident direction is like this. The first cylinder produces a shadow. The first cylinder produces a shadow like this, or like this better, and this shadow eclipses or leaves this part of the second cylinder in the shadow region. And this means that the conventional way to determine illuminated or shadow regions, we detect here, observe that this is the normal to the surface here, and this is Ki. Here we have a surface section that is shadowed by the first cylinder, but however it agrees with the criterion it agrees with the condition for illuminated regions, because this condition for illuminated regions does not take into account the shadowing by other parts of the object. So this is the difficult part of physical optics. When you have objects that are not convex, that they have complex shapes with many concavities or different, or the object divided in different parts, then some parts may shadow other parts. And this is a very important and difficult problem, because you have to identify the parts of the object that are shadowed by other parts and agree with the condition unit normal dot product with incident direction smaller than 0, that would be illuminated if this part was isolated, but since it is not isolated and it is shadowed by another part, in practice it is shadowed. So this is the difficult part, and in fact very, very difficult part in the programming of physical optics. Here we have some results. We have the physical optics in red color compared with method of moments for a cylinder, a circular cylinder, two-dimensional, because it's the easy problem, two-dimensional circular cylinder in TM case, with TM polarization and TE polarization. And we have made the computation, the method moments computation for two cylinder radius, for a radius of 10 lambda or 100 lambda. We can see that for radius 100 lambda in green color, no, it's not the method of moments computation, sorry, it is the analytical solution. It is the analytical solution, not the method of moments. The analytical solution for radius 100 lambda is almost exactly equal to the physical optics solution. In fact, physical optics is a high frequency approximation, so it works very, very, very well when the radius of the cylinder is very large compared with lambda. And we can see clearly that the current is different than 0 on the illuminated region. The illuminated region is, let's change the color, red color here. The illuminated region is this. This is the illuminated region. Okay, so in this region the current is different than 0, equal to the tangent component of the magnetic field. This is normal, twice the tangent component of the magnetic field. So it is normalized with the amplitude of the maximum amplitude of the magnetic field, so it is equal to 2 when the magnetic field, incident magnetic field, is parallel to the surface, and 0 when the incident magnetic field is perpendicular to the surface. But now we also have 0 and the shadow region. This is the shadow region. This is with the shadow region, and we have 0 here. If we compare with the solution, with analytical solution for radius 10 lambda, well, it is similar, but now the shadow is not so deep. Remember that the larger the cylinder with lambda, the deeper is the shadow. So the shadow is not so deep, and we have some smoother transition from the current in the illuminated region to the zero current in the shadow region. So the approximation is not, for a radius of 10 lambda, is not as good as with 100 lambda, but anyway it's quite good. It's good enough for practical purposes. Even for less than that, even for radius of maybe 2 lambda, or 1 lambda, it's good enough. But what's important is that the higher the frequency, the more accurate the physical optics approximation. In the TE case, we also have in red color the physical optics approximation. Now we can observe that in green color we have 100 lambda radius, the solution for 100 lambda radius, the analytical solution. It is close to the physical optics approximation, but not as close as in the TM case. And the same happens, but worse, for radius 10 lambda. The current at the shadow region is much smaller than in the illuminated region, but is not completely zero. Why? Because there are creeping waves. Remember the creeping waves in the TE case, the creeping waves that turn around the cylinder in the shadow region. These creeping waves make the induced current in the shadow region different than zero. But the larger the cylinder, the faster attenuation of the creeping waves, and the closer to the physical optics approximation, that in fact physical optics approximation is an approximation for infinite frequency. So let's say for optical frequency, in the sense that a common life object has millions of lambdas compared to the lambda of light on the optical region. Okay, so physical optics is an approximation valid for very high frequency, but anyway it works quite well for radius of for surface sizes and radius of curvature of just a few lambda. Anyway, it's not able to predict the creeping waves in the TE case, but the larger the object compared with lambda, the less important are the creeping waves. In the physical optics integral, there are clearly two different parts. There is first a function that is given by the magnitude of, well, the magnitude of the induced current, the physical optics current, that is slow varying. But then we have a phase that is fast varying when k is large, and then the surface, the size of the surface, is large compared with lambda. We will, in the following, we will say that k goes to infinity, meaning that we are in very high frequency region, and then the size of the object is large compared with lambda, just because lambda is very small. So in this case, it is the frequency is large enough to have a wavelength much smaller than the size of the object. And we summarize this as k goes to infinity. In this case, the phase varies so fast, and the size of the object is so large compared with the wavelength, that there are many phase cycles within the region of integration. So if we have to integrate this phase from in all this interval, the phase has a very fast variation. So there are many phase cycles, and in phase cycles, you know that the positive phase cancels the negative phase. So we have positive phase, negative phase alternating very fast, and the positive parts cancel the negative ones because the amplitude of the induced current G is slow varying, so it is approximately the same in the positive and negative parts of the phase, allowing the cancellation. So the integral would be 0, except from the fact that there is some region where the phase is stationary. So there is some part of the object where the derivative of the phase, this shows k times f, which is the k times f is the phase of this integral, or minus k times f, doesn't matter, is the phase of this complex exponential. So at some point the derivative of the phase is 0, that is, the phase is stationary. This is called the stationary phase point xs here. This is the stationary phase point xs, s from stationary, where the derivative of the phase is equal, at this point, the derivative of the phase at the stationary phase point is equal to 0. So in this point, there is no cancellation between the positive and negative parts of a period of the phase. In this case, we have, for example, we have to compute the area under the curve. We see that the red and green areas cancel out, but there is a remaining part in blue color coming from the neighborhood of the stationary phase point. So we will see later that it is this point where a specular reflection occurs. And we will show later that all the contribution from the physical optics all the contribution to the physical optics integral comes from the stationary phase point and only from the stationary phase point. I will show you this mathematically. The integral that we have is of this kind. We have a slowly varying phase and, a slowly varying amplitude and a fast varying phase. We can see this here and we can see this here. This is the slow varying part, G. Sorry. This is the slowly varying part of the integrand, and this is the fast varying phase of the integrand. So we have a slowly varying amplitude and a fast varying phase. Okay, this is the form of integral that we have: a slow varying amplitude and fast varying phase. Okay, now we just multiply and divide by this. So in fact what we are is just taking out the part corresponding, the phase corresponding to the stationary phase point, and here we have the subtraction of the phase at any point minus the phase of the stationary phase point. This is something normal, and we observe that this is highly oscillatory, has very fast phase variation for all points that are away from the stationary phase point, and of course very large k going to infinity, when the wavelength is much smaller than the size of the integration interval. Then we have this cancellation, except in the we have this cancellation in this region, so the only contribution comes from the neighborhood of the stationary phase point. So here what we do, we remove all the pairs that cancel out and we retain only the neighborhood of the stationary phase point. Since at the neighborhood of the stationary phase point the amplitude of the integrand is slow varying, it is approximately equal to the amplitude at the stationary phase point. So we can take it out from the integral. Okay, this was Jx, but remember that G is slow bearing, so Gx is approximately equal to Gxs in the neighborhood of xs, and we can take it out of the integral because now we are integrating only in the neighborhood of xs. Now we do a Taylor series of this. Taylor series of s, essentially subtracting the value of f at the stationary phase point, and the Taylor series is this, because it would be the Taylor series of s would be equal to f of the Taylor series of x centered at xs should be equal to fxs, which is already subtracted here, so it doesn't go here because it's already subtracted, plus the derivative of f that is at xs, which is 0, so this term vanishes, and the third term would be the second derivative of f at xs over 2 factorial of 2, which is 2, okay, times x minus xs squared. So this is the Taylor series of the exponent, the Taylor series of the phase. Okay, this is what we got. This is the last expression in the last slide. This is what we got. And now, since the region away from xs has a negligible contribution, we can extend again the integral from minus infinity to infinity, because what we are adding are parts with a negligible contribution where the phase cancels out. The difference with the last expression here is that we were integrating in the actual surface limits. Now we are integrating from minus infinity to infinity. It doesn't matter because just it is what we have added, all the interval that we have added up to infinity and minus infinity has negligible contribution due to the phase cancellation. We have replaced the phase by the Taylor expansion of the phase, Taylor series of the phase, and we have taken out the value of the slow varying amplitude of the current out from the integral. Okay, but now this integral has an analytical result that is just the square root of pi over a, where a is the constant multiplying the variable square. Essentially here a would be a j k over 2. Okay, so if we replace a by k over 2, we get this. And of course, with this part that we have taken out of the integral, we get this high frequency approximation of the physical optics integral. And this is called the stationary phase approximation. And it's very important because it just shows that in order to compute the integral, the physical optics integral in the high frequency region, we don't have to sum the integrand for all the integration points. We only have to account for the value of the integrand and the stationary phase point. This is just the integrand, the induced current, physical optics current, times the phase exponential, evaluated at the stationary phase point, times a factor that comes from the curvature of the surface. Here, the second derivative of the phase at the stationary point is essentially related with the curvature of the surface, as we will see in the example next. But I stress again the most important result that we have obtained, local diffraction. The overall contribution, the overall computation of the physical optics integral depends only on the value of the integrand at one point, the stationary phase point, plus some factor depending on the curvature of the surface at this point. And we will see this with a very simple example. This is a finite cylinder of length L in the Tm case. So we integrate the physical optics current times the Fourier transform exponential, complex exponential, surface integral in C coordinate from 0 to L. L is the length of the cylinder. In alpha coordinate here, alpha is like phi, but in fact alpha is pi minus phi coordinate. In alpha coordinate we integrate from minus pi over 2 to plus pi over 2 because we are integrating in the illuminated region of the surface where the physical optics current is different than 0. So this is already the integral here, the projection of the current on the transverse plane is equal to 1, so there is no trigonometric function due to the projection because the current already has a set component, the radiation vector has set component. In monostatic RCS, the observation distance is minus the incident distance, the observation direction is minus the incidence direction. The incidence direction is along positive the incident direction is along positive x, so the scattering direction or observation direction is along negative x. So here we have just the observation kx equal to minus k because we are observing with minus kx. So in this observation direction, the observation vector r is already perpendicular to the current, so there is no trigonometric function due to the projection. All this has been computed here in this very simple Tm case, and the physical optics current is twice the tangent component of the magnetic field. The magnetic field magnitude is the electric field magnitude over the wave impedance. Then the projection of the magnetic field on the tangent plane is this cosinus of alpha. When alpha is 0, the magnetic field is already tangent to the surface, so cosinus is equal to 1. And when alpha is pi over 2, the magnetic field is perpendicular to the surface, so the tangent component of the magnetic field is equal to 0 and the cosinus is 0. Okay? And then we have the incident, the phase of the incident plane wave here, because the incident plane wave propagates along positive x direction. So we replace the physical optics current within the integral. We take the constants out of the integral, and we write the integral in the form of the stationary phase. Remember here the form integral of j is the amplitude and the phase k minus kf. So we write the integral in that way, and we identify essentially g with the cosinus of alpha, and we identify f with 2x prime. So function f, the phase function, or kf, is k 2x prime. F is 2x prime. So x prime is clearly a, the radius of the cylinder, cosinus of alpha. So f is minus 2a cosinus of alpha. f prime is 2a sinus of alpha, clearly the stationary phase point is at alpha equal to 0. So, because at alpha equal to 0 the derivative of f is 0, so the stationary phase point is alpha s equal to 0. Clearly the stationary phase point is clearly this one here, alpha equal to 0. This should be the stationary phase point, let's say alpha s, sorry, not xs, but alpha s. Okay, and the second derivative of f at alpha, the second derivative of s is 2a cosinus of alpha. So at the stationary phase point, the second derivative of f at 0 is essentially 2a. So we compute the scatter field using the stationary phase formula that we obtained in the slide before, as g at 0, g is the cosinus of alpha, so g at 0 is essentially 1 times all the constants. So we have here all the constants, and for the computation of the integral, j0 here, yes, j0 is 1, because cosinus of alpha at alpha equal to 0 is 1, and what remains is the square root of 2 pi over k, second derivative of s at the stationary phase point. The second derivative of f at the stationary phase point is 2a, because the stationary phase point is alpha equal to 0, cosinus equal to 1, so 2a here, and we just simply cancel the k's and the pi's and etc., and we get this. This is the scatter electric field over the incident electric field as a function of the radius of the cylinder, the frequency, and the length of the cylinder, and the distance of observation for monostatic observation, for observation direction opposite to the direction of incidence. So this is what we got. This is what we got in the slide before. We compute the three-dimensional RCS, and the three-dimensional RCS is equal to 4 pi r squared, and then the square of the scatter field over the incident field. We replace the result that we obtained, and the three-dimensional RCS is Ka L squared equal, if we replace K by 2 pi over lambda, equal to 2 pi A over lambda, which is the electrical radius. This is the electrical radius, the radius compared with lambda, and L squared. L is the length of the cylinder. And now we remind that for the two-dimensional cylinder, we obtain an analytic result for the RCS valid for any radius of the cylinder compared with lambda, but we did a large argument approximation of the Bessel functions, and in the high frequency region we obtained that the two-dimensional RCS of the infinite cylinder was pi a for very large radius in the very high frequency region. And this was obtained as an analytical result using the series of Hankel functions and Bessel functions as an analytical result, and then in the limit of high frequency using the large argument approximation of the Bessel and Hankel functions. And this is exact for very large frequency. And remember that there was, in the first slides of this chapter, I presented an approximate relation between the three-dimensional RCS of a cylinder of length L, where L is large compared to the wavelength, and the incidence is perpendicular to the axis of the cylinder. This formula relates the radar cross-section in 3D with the two-dimensional radar cross-section of the infinite cylinder, as the later times L square over lambda. Here we can clearly see that if we replace the two-dimensional RCS with pi a, here we put pi a, what do we get? 2 pi a over lambda L square. We obtain exactly the same result. So the result that we obtain first with physical optics approximation, which is already an approximation, then doing a stationary phase approximation within physical optics approximation, we got this. And this agrees exactly with our analytical exact result for the two-dimensional RCS of the infinite cylinder. Then doing a high frequency limit in this analytical result. And we obtain pi a for the two-dimensional RCS, which is exact in the very high frequency limit. And then using this approximate formula, we obtain exactly the same as from the physical optics integral. And this shows that since this result was obtained with physical optics integral, but also with a stationary phase approximation, and a stationary phase approximation, remember, that is local scattering because it only computes the integrand, the physical optics current. It only computes the physical optics current and the phase of the physical optics current contribution at the stationary phase point. So including only computations at the stationary phase point, we obtain the same result as was derived from analytical solution of the canonical objects using the expansions of Hankel and Fourier and Bessel series. So this just confirms the local scattering assumption. This just confirms that scattering is truly local. This was a good assumption because, and we have confirmed it mathematically with a stationary phase approximation and also with a very simple example. So to show you an example for a general surface in which I will show you that the stationary phase point is also the specular reflection point, this is something that I mentioned before, and now I will show it to you. This is the source of the field. This is the observer. This is the surface reflecting the field. So we have to integrate, the physical optics integral integrates the contribution of the current at all points of the surface. So for example, here we have an incident field. Here we have an incident field, okay? This incident field produces here a physical optics current, and this physical optics current produces a contribution to the observer. Then we have another point here where the incident field produces a physical optics current, and this physical optics current contributes to the field observed by the observer. And the same here and the same everywhere, the same here, okay, the same for all points on the surface. And what we do is we integrate the contribution of all the surface points, okay? We integrate all the contributions, okay? But we can observe that the total phase, including the phase of the Fourier transform exponential and the phase of the incident field that is within the physical optics current, remember here that when we replace the value of the physical optics current, the physical optics current has some phase due to the phase of the incident field. The physical optics current is twice the tangent component of the magnetic incident field. The magnetic incident field is a plane wave. It has a phase. So we have a total phase, which is the phase of the incident field plus the phase of the path due to the path from the from R prime to R, from the point on the surface to the observer. So the total phase comes from the summation of the incident field's phase, the field from the source to the surface point, incident field phase, plus the phase from the surface point to the observer. We can see this also in the example here. In the example here, the physical optics current has some phase, the radiation integral has also some phase. The first is due to the path. The phase of the physical optics current is due to the path from the source to the surface point. The phase of the radiation integral is due to the path from the surface point to the observer. We have to sum the two phases, and in this case, it was a monostatic case. We obtain twice the incident field phase, because in this case the observer is in the opposite direction. But in general, what we get is the phase due to the path from the source to the reflection point plus the path from the reflection point to the observer. So the function f is the path, the total path from the source to the reflection point and the reflection point to the observer. And when we multiply by k, and when we multiply this by k here, with this k, what we get is the phase. But essentially f is the path, total path from the source, the reflection point at the surface, and the observer. And we can see that this path at some end of the surface is large. Then the total length of the path decreases. It decreases even further. It reaches a minimum, and then it increases again. So then the total path increases again. Okay. So there is a minimum of the path. The f, which is the total length of the path, is minimum at some point, and the point of stationary phase, because the point of a stationary phase was defined as the point where the derivative of the phase is equal to 0. The phase is equal to k times the path length. So the point where the path length has the 0 derivative is a minimum, is the stationary phase point. We have computed mathematically the radiation integral in this case as the contribution of only the stationary phase point using stationary phase approximation. This is because the stationary phase point is the point that agrees with Snell's law. At the stationary phase point, the angle of reflection is equal to the angle of incidence, exactly equal. This is something that can be proven also easily, but we can observe this also in practice. For example, imagine that you are illuminating a perfectly metallic sphere in a dark room. You are illuminating with a torch a metallic sphere. What do you see? You only see a point on the sphere. You have a sphere here. You have your torch here producing some light. You are observing here, and you only see a bright point here at the point of a stationary phase. You only see a bright point here, and the rest is black. The rest is completely dark. You don't see the sphere. You don't see the whole sphere. You just see only one point. You just see only the stationary phase point. You see nothing else than the stationary phase point. And you must do this experiment in a very dark room, because if you have ambient light would reflect on the whole sphere surface and you would see the whole surface. If you are careful to do the experiment in a dark room with dark walls, with no other source of light than your torch, you will not see your sphere. You will see only a bright point, the stationary phase point, which is the specular reflection point, the point of minimum path length between the source, the reflection point, and the observer, the minimum path length that corresponds to the minimum phase, that is the stationary phase, the minimum phase here, observe here the minimum phase here, this is the specular reflection point, or stationary phase point. So this point is the point of specular reflection, the point where the angle of observation is equal to the angle of incidence according to Snell's law. And this is a very important concept that you have to keep in mind. Well, we have seen that the main contribution to the physical optics integral is the specular reflection point, but in fact it is not the only contribution, because the cancellation or the phase cancellation, where we have very rapid oscillation of the phase cancellation stops at the surface integration limits. Observe here that we cancel, for example, this negative phase with this positive, negative and positive cancel out, but you need this integral extending to infinity. But if you stop the integral somewhere, for example, if you stop the integral here, you have a positive phase that doesn't have the negative counterpart to cancel it. Okay? So we don't have the cancellation, or may not have the cancellation at the surface integration limits, and may have a net contribution coming from the surface integration limit. So apart from the contribution at specular reflection points, this is contribution number 1 here. Number 1 is the contribution from the specular reflection points. Okay, the specular point with reflection of angle of observation equal to angle of incidence, Snell law, specular reflection point, which is, as we have seen, the stationary phase point. But however, at 2 and 3, we have integration limits. We have the end of the region of integration. And here we can have net contributions where the phase has not been cancelled. Okay? This is in practice what happens with Gordon integral. Remember the Gordon formula here? Remember that using Stokes theorem for a planar surface, we got the surface integral equal to the integral at the edges. This is because in a planar surface we have no specular reflection point except when the incidence direction is perpendicular to the surface and the whole surface is specular. Otherwise, when you have a direction of incidence and a direction of observation, the integral doesn't have a stationary phase point. The phase monotonically increases or decreases, but there is no point with the derivative of the phase equal to 0. In this case, there is no contribution from the specular reflection point, and the whole contribution comes from the limits, here, here, and here. The whole contribution comes from the limits, because this is just a summation of the integral along the edges. Okay? So there are clearly two contributions. The contributions of the specular reflection points. The specular reflection points are very clear, for example, in the case of curved surfaces. Remember here we had this specular reflection point at alpha equal to 0. And here we have the specular reflection point. But all these cases are cases of curved surfaces. But in planar surfaces, it's different. In planar surfaces we may not have the specular reflection point, and the only contribution is from the geometrical limits of the surface. So we have the specular reflection point that exists only in curved surfaces, and in planar surfaces either the specular reflection point doesn't exist or the specular reflection point is the whole surface in the case of perpendicular incidence. And then the contribution of the limits. But here we split the limits in two. We have the limits that are really geometrical limits, contribution number 2, geometrical limits to the surface, that is the surface end, the point where the surface ends. But we also have some artificial limits, because remember that we have set in physical optics approximation, we have set the current different than 0 at the lit region here, and the current equal to 0 at the shade region. So this is an abrupt transition between the lit region and the shadow region, and this limit of the integral is not a limit corresponding to a physical termination of the geometry. Like, for example, imagine that you have a curved plate. You have a plate here, and the plate terminates here, and the plate terminates here, okay? This is the physical limit of the plate. This is contribution number 2. But we can also have contribution number 3 here, and the artificial limit between the lit region and the shadow region, because it depends on the polarization of the current. But for example, in the TE case, observe that in the TE case, the current decreases smoothly from the illuminated region to the shadow region. But our physical optics approximation has an abrupt termination, here and here, that will leave some cycles of phase without cancelling. This will produce this non-cancellation of this positive phase with the next negative one. However, this is what happens due to the artificial abrupt termination of the physical optics current. But in practice, the physical optics current is smoothly decreases smoothly. So if the current decreases smoothly, what we have is that here we have a smooth decrease of the current. It should be the magnitude of the current. This is a smooth decrease of the current. So and remember that the phase variation is much faster than the variation of the amplitude of the current. The amplitude of the current is slowly varying. So in practice, the variation of the amplitude would be much slower, like this. So then this very slow variation of the amplitude of the current permits the cancellation of all the phase cycles with the next one, okay? Sorry, not this, this, and this, etc. This and this, etc. Okay, this is due to the fact that the current has a slow variation. So this contribution number 3, the contribution of the artificial shadow boundary, in fact, is a spurious contribution. More about this later. It's a spurious contribution because the current, the actual current, doesn't have this abrupt step termination between the illuminated region and the shade region. As I said before, for a planar surface there is no specular reflection point except in the direction of specular reflection. So there is no except in the case where, if this is our planar surface, if except in the case of a specular reflection, and in this case the whole surface is a specular reflection point. Otherwise, for other directions of incidence, what the important thing are the contribution of the, because the whole surface is a if you are in the specular here also, if you are in this biostatic case, also if you are in the specular direction, the whole surface is specular. But if you are in another direction, if you are in another direction or this, then nothing is specular, and you must compute the integral not from the specular reflection point but from the surface integration limits using Gordon's formula. Okay, this is what I said also in the slide before, that for planar surfaces in many cases you don't have a specular reflection point, and you must use Gordon's formula to compute the contribution of the edges or the limits of the surface. So this is contribution from the shadow boundary, the contribution number 3 in the previous or two previous slides, is spurious because it doesn't exist actually it doesn't exist in the exact solution. Okay, because as I told you before, the induced current decreases smoothly from the physical optics value at the lit region to 0 in the shadow region. This is what I showed you before using the exact results for the cylinder current in the TE case. I showed you this before using the exact results here. Okay, so you can see the idea in this slide. This allows this smooth transition of the actual current between the illuminated region and the shadow region. This smooth transition allows the cancellation of positive and negative this is negative phase cycles. Okay, this smooth transition allows the cancellation. So this contribution of the artificial shadow boundary is spurious. So the contributions are 1. Specular reflection point. 2. Geometrical limits of surface. Okay, but then the artificial shadow boundary contribution number 3. This is spurious, and this contribution is only in physical optics approximation. If you compute the actual field using, for example, method of moments, or using in the case of a cylinder the analytical solution for the canonical geometry, in the actual exact field, what do you have? You have the contribution of the specular reflection point, the contribution of the geometrical limits of the surface, and then the contribution of edge diffraction at the edges that limit the surface. And this is something that we will see at the end of this chapter, the contribution of edge diffraction. But instead, physical optical approximation doesn't account for edge diffraction because it uses tangent plane approximation that assumes an infinite surface. And instead of edge diffraction, physical optics includes this spurious contribution that comes from the artificial ends of the surface. So, what are the limitations of physical optics approximation? Well, we are using tangent plane approximation. Of course, our surface will be close to a tangent plane, our surface will be close to a tangent plane if they're similar to a tangent plane if the radius of curvature is very large. However, if the radius of curvature is small, the current in a cylinder or a sphere of a small radius of curvature will not be similar to the current in an infinite plane. Then the physical optics approximation will fail. In practice, it works quite well for radius of curvature larger than, let's say, 1, or I will say 1 lambda, but even with half lambda, it's not bad. Even with half lambda. But anyway, to be more rigorous, I will say 1 lambda. So first, we need a surface of large radius of curvature compared with lambda. Second, it will fail at edges because we are using, again, I repeat that we are using tangent plane approximation. So tangent plane approximation is not valid at edges because at an edge, the surface is, or the geometry of the edge is completely different to that of a tangent plane. So here again we have a case where physical optics approximation will fail. At the end of the chapter, I will tell you how to compute the contribution from edges. And all the remaining scattering effects are not taken into account by physical optics. So diffraction, surface discontinuities, material discontinuities, body ends, tips, surface waves, whatever any other scattering effect that you may think of is not accounted for with physical optics. Of course, creeping waves. Creeping waves are also neglected by physical optics because you know that physical optics assumes zero current in the shadow region, and in the shadow region we may have creeping waves. So these creeping waves are completely neglected by physical optics. So there are many cases in which, and many scattering effects for which physical optics doesn't work. But anyway, and of course, I forgot this, and of course the contribution of the artificial shadow boundary, that is also a limitation of physical optics because it is a spurious contribution computed in physical optics. But anyway, there are many cases when it fails. But anyway, it's very good. It's very good because it computes with quite good accuracy the main contribution, because the main contribution is the contribution of large surfaces electrically large with large radius of curvature. And as I told you before, by the end of the previous lesson, the surface reflection, large surface reflection, is the main and most important contribution to overall scattering, and this is computed very well by physical optics. And a clear example is the computation of parabolic reflector antennas. In fact, the most software for computing reflector antennas are often too large compared to the wavelength to be analyzed by method of moments, unless you have a very powerful computer and a very efficient fast solver. Otherwise, you must use high-frequency methods to compute the radiation of a reflector antenna. And physical optics is very, very good. In physical optics, you have your feeder, you compute the incident field on the surface of the reflector, you compute the physical optics current, and you compute the radiation of the physical optics current. And the result is very, very good, and physical optics has been used for many, many years to compute the radiation pattern of large reflectors. And in fact, one of the best software, maybe the best one for analyzing reflector antennas, that is developed by a Danish company, and it's probably the best software for reflector antennas in the world, uses of course physical optics. To finish with the physical optics, just a few examples. Here we have a two-dimensional strip. The strip is two-dimensional, so this is infinite. In Z direction, it is infinite, okay? And it has a width. W is the width of the width of the strip. And we have TM and TE cases. In TM case, the electric field is parallel to the Z axis. In TE case, the electric field is perpendicular to Z axis. The strip is here. We compute the scattering using physical optics. This is very easy because in this case, the projection of the component of the magnetic field tangent to the surface is constant in the whole surface, so the magnitude of the physical optics current is constant in the whole surface, and you don't only have the phase variation of the physical optics current. The incident field is a plane wave, so you have a progressive phase of the incident field along the plate, the strip, the surface, and this is very easy to integrate. The integration of the integral of a progressive phase in a planar region is a sinc function. You already know that. So the physical optics integral is trivial, and this is the result. The whole derivation of this is in Balany's book. This is just copied from Balany's book. You have the whole derivation there. And this is the plot of the biostatic RCS for a direction of incidence equal to 120 degrees. And then we have the specular scattering direction at 60 degrees, and we can observe that the maximum of the pattern is at 60 degrees, which is the specular direction. By the way, the larger the surface size, the larger the surface, the more directive is the radiation pattern, and the more concentrated is the pattern, the narrow beam of the pattern at the direction of specular reflection. In practice, for infinite width, you would get at delta, you would get only all the field in the specular reflection, that is the reflection of the plane wave in an infinite plane according to image theory. Okay? And if the surface size is small compared to the wavelength, not compared to the wavelength, this is two wavelengths, but if the surface size is smaller, then the pattern is less directive, and but if the surface size is too small, then of course we will have problems with the validity of physical optics approximation. But anyway, this is, in the case of a large surface like this of 20 lambda, the green color one, this is very close to what you can compute with method of moments, the exact solution. Very close to. You would only have to add the contribution of the edges. And this is the monostatic RCS in the case of two strips, one strip of 10 lambda and the other of 2 lambda. Of course, the larger strip has a narrower beam because it concentrates more. It is more similar to an infinite plane that concentrates the reflection in the direction of specular reflection. In fact, you can recognize here the pattern of an aperture antenna, because obviously the physical optics current here, the physical optics current is a current in a plate, and when you integrate the radiation of a current in a plate, it is similar to the radiation of a aperture antenna having this the same area as the plate. And the same in 3D. Now in 3D we have also TE and TM cases. In the here, let's say, this TE and TM cases are defined with respect to x direction. here x direction is perpendicular to the paper, so TEX has electric field perpendicular to x direction, so electric field is in the plane of the paper, and TMX has magnetic field perpendicular to x direction, so electric field is parallel to x direction. So in fact, in terms of the usual reflection coefficients, TE case would be the case of parallel polarization, and TM case would be the case of perpendicular polarization. Polarization parallel to the plane of incidence or perpendicular to the plane of incidence. We can compute very easily the expressions of the radar cross-section in this case, because again we have the magnitude of the physical optics current is constant along the whole surface. The magnitude is constant, and therefore for constant magnitude we only have the phase variation. The phase variation is a linear phase along the surface, and the integral of a linear phase is a sinc. You can see the sinc here. This is trivial. You have in the assignments you have to compute a similar case, but for a circular plate instead of a rectangular plate. The rectangular plate is very easy. The circular plate is more difficult because you have to use wave transforms between plane wave and cylindrical waves. You have to use wave transforms, and Bessel functions is more difficult, and for that reason the assignment is to compute the physical optics RCS for a circular plate. But however, if you find this assignment too difficult, just solve the rectangular plate. Solve this. If you are able to obtain this instead of the circular plate, this is for the rectangular plate. This is very easy. Of course, you will not have 10 over 10. Maybe you will have 5 or 6 over 10. But you have something, okay? So, just to help you just to help you, in case that you feel that you are unable to solve the more difficult case of the circular plate, just solve the rectangular plate, obtain these results, make the derivation of these results for the RCS, and you will have maybe a 5 over 10, but you will have something. Well, the plots for the previous results are these. Again, we have the maximum in the specular reflection direction. Here the direction of incidence is 30 degrees with respect. This is 30 degrees with respect to this is the unit normal. So we have a incidence direction 30 degrees with respect to the normal of the surface. So the specular reflection according to Snell's law is also at 30 degrees, and we can see here the maximum of the reflected field at 30 degrees. And in the monostatic case we have something similar.